So for the edge part, we thought like right the competition was the competition evaluated on basis of the GPU servers. Uh, so we thought like we should go one step further. The competition's goal was already finished, so we thought like maybe we should go one step further and deploy this on actual edge hardware. So we did this, and we faced a lot of problems when doing this. So we tried to split all those problems into main these four quadrants, which we think are the prerequisites for deployment on any type of edge hardware. So Ben will go through the quadrants of optimization and model deployment, and sorry, Naveen will go through the quadrants for model deployment and optimization, and Ben will go for physical and product related quadrants for the prerequisites of deploying on edge. Before that, we have a short video which we did for the field testing. So I would like to play this. I hope so the audio is there.
Yeah, we are recording.
Now we are recording MLT demonstration, HAI demonstrations. Hey, UV.
Hey.
Say hi, Ben. Hello.
This is like random. Last week we
record Naveen.
Went around the Tamagawa River in Kawasaki, and we thought like,
hey,
maybe
hey
we
guys,
should deploy this
on
hardware.
Hello.
Yeah,
stop. I will. Hey, hello.
So here you can see like the board as a Jetson Nano is in the basket, and we have fixed a camera on the bike. And so this was the place for setting up and testing, and then I will go around the town by bike, and here's a running test. So I'm not sure why you start to run after the bike to film the bike, but we can have some funny footage.
Yeah, it was like a moment of directors. Like we thought we were like a movie directors trying to shoot the same scene.
What is weird is that sometimes we start to film Alicia instead of the bike. Not sure why.
So it's like one day.
Sorry for this awful video footage. It was fun to do.
So, yeah, I think it was really fun. Like, I mean, let me hand over to Ben. Let me hand over to Naveen, who will start explaining whatever the prerequisites or the blockers which we had on hardware. Yeah, Naveen, take it over.
Yeah, hi, thanks, you. So I will talk about the model deployment and optimization. So basically, I will talk about the challenges and the success we had in the deployment of the on the edge devices. And actually, we experimented with many edge devices. So can you go next slide? There is one more before that. Oh, that's missing. Anyway.
Oh, sorry.
Yeah. So yeah, this one.
Oh, sorry. Okay, I will get this first.
Yeah. So these are the hardware actually we tested with and experiment with. So the first top one is we try with the neural computer stick with the Raspberry Pi 4. And we tried with the Jetson Nano, of course, and we tried with another NPU based hardware, that is the neural processing unit. So these are from the Rockchip, that is the bottom left. And we tried with the ASUS Tinker Edge also. So that is on the bottom right. So I will talk one by one. So did we get some success, or what was the challenges? So can you go to the next slide? Thank you. Oh, yeah. So first, there were challenges to moving the model and the implementation from the SciNet to the edge. So on the SciNet, we had the image resolution that is 1936 by 1216. So we trained the model on this resolution, and we also were doing the inferencing on this resolution. But going to the edge, this resolution was too high to handle with, because there were many challenges like memory issue of the edge devices, and also video processing was actually also demanding. So we retrained the model with 640 by 360 resolution, and then we deployed to the edge device. Then for the deployment on the SigNet, so we had the cloud, we were running everything in the cloud in their container, and actually we did not have any access of that cloud. So we just submitted our solution in an implementation to the cloud, and SigNet actually run automatically there. But we had the specs, they use the Tesla V100 GPU there with the 5120 CUDA cores. But on the Jetson Nano, we had to actually move the model to the, lower end, low power device. So we had only 128 CUDA cores. And GPU memory, and on the SigNet, we had the 16 GB dedicated Tesla V100. But on the other hand, on the Jetson Nano, we have only 4 GB of shared memory. So the memory on the Jetson Nano is shared between the CPU and GPU. So you have to actually, there is no logical partition. So whichever can, gain the access of the memory, they can actually use that. So I will talk in the next slide how we overcome the memory issue in the Jetson Nano. And for the input batch size, so actually for the competition, we were feeding 2 images. Input batch size was 2 actually. But for the edge devices, we have to, reduce that to the batch 1. And the inferencing time for the SigNet was 2 frames per second actually, we achieved. So actually for the test video, they provided, I think, 130 seconds of test video, and each second comprised of the, I think it has 5 frames. So it was total 150 frames, and we actually did the inferencing within around 75 seconds. So that comes out 2 frames per second. But we achieved 1 frame per second on Jetson Nano. That is, good, because if you think about the Keras RetinaNet, it's a bulky model for edge device. For big GPUs, it's okay. But still, we were, did not do any kind of optimization for the SigNet. We were just busy with the submission, and what we got was actually better than others. But this time, deploying on the edge device, we faced challenges for the frame rate optimization. So we did many optimization on that. So next slide, please. Yes. So for the model deployment, actually we tried with these 4 devices. So Jetson Nano, Raspberry Pi 4 with Intel Neural Compute Stick 2, RockPi N10, that is the Rockchip neural processing unit. And we tried with the Google Coral USB accelerator and ASUS Tinker ST. Actually, these both are actually same thing. Both are using the Google Coral TPU. So for the Jetson Nano, actually, we had the success because there was no conversion for the model, and we ran the model as is without any change, and it was good actually. So Jetson Nano is actually good for deploying any kind of model which runs on your laptop or on cloud. You can easily move to the Jetson Nano. For the Raspberry Pi with the Neural Compute Stick 2, we had the success, but the problem was you have to convert your model to the intermediate representation of the OpenVINO. So OpenVINO is a framework which Neural Compute Stick 2 uses. So you have to convert your model to that format, and then you have to deploy to the Neural Compute Stick. And then the performance was almost similar to the Jetson Nano. Then we tried with the RockPi N10, but we had the problem with the conversion of the model to their framework specific format, because you have to again convert the model to that specific board format. So they provide actually some kind of compiler for the conversion of the model. But since Keras RetinaNet uses some kind of custom operations, so that were not directly convertible to the NPU, which RockPi N10 uses. So we could not test it on that board. And on the Google Coral and the ASUS Tinker ST, we are still working on that. So the problem was we faced you have to convert the Keras ReturnNet model, so that is in the Keras, into a TensorFlow Lite. So there were some issue actually on GitHub, so they are actually working on that. So when they will fix that issue, so we will try that on Google Coral or SUStinker ST. And next is the optimization. So optimization is actually very important when you deploy the model to the edge devices, because they have actually low power devices and they have less memory than your laptop or your cloud solution, and also the software actually. So when you use the software, so that should be actually natively compiled. So what we did actually, so NVIDIA, which provides the Jetson Nano board, so they have the libraries for the, which is natively compiled for the this particular Jetson Nano board. So actually we use those natively compiled library. You can actually install the GS streamer or OpenCV directly using a command line like apt or some PIP command, but those will be not optimized. Actually, you need to find the optimized versions and install on that. So you will get much more performance in CPU plus GPU plus memory. I mean, there are three things which are involved in these kind of things. So we use those kind of library to the optimized library. And then we faced one challenge when we were running the model. I mean, when we started running the model on the Jetson Nano. So the memory was actually, I mean, we were getting some kind of memory overflow issue. So Jetson Nano has a 4 GB memory, which is shared with the CPU also. So when you start CPU with GUI, so it takes around 1 GB of memory. And 3 GB was not sufficient to run the Keras ReturnNet on the Jetson Nano. It was demanding around 3.6 GB. So what we did actually, we removed the GUI in the installation, and then we started the model, and also we switched down all those not important programs which are running by default. So keep the memory usage low, and then it was okay. So that was one challenge we faced with the Jetson Nano, but otherwise actually it was like piece of cake to move your laptop or cloud model easily to the this Nano device. And then we started working on the conversion to the TensorRT. So what problem we faced in the Jetson Nano was the frame rate actually. So we could achieve only 1 frame per second. That was, I mean, better than, I mean, if you compare with the cloud where we got 2 frames per second, but that was the unoptimized version of the model. So that was okay. But on Jetson Nano, we got 1 frame per second, but we wanted to make it more, I mean, more performant. So the TensorRT is a framework, actually, the SDK, which NVIDIA provides. So it compiles the model, existing model, to native CUDA-based optimization. So it can run your existing model maybe 4 times, maybe 10 times, depends on the model. So it can actually improve your inferencing rate. But unfortunately, we could not, I mean, convert it into the TensorRT currently, because there are some unsupported operations, ops, in the Keras implementation, which could not convert it directly into the TensorRT. But actually, we are still working on these things, and we hope we can convert it into the TensorRT and improve the frame rate. Yeah. And then one thing, so this is the board actually, if you can see. So this is the Jetson Nano. Can you see this? Or maybe my background.
The background, maybe you can little bit hold down in front of your shirt. Yeah, I think that is.
Yeah, so this is the board actually. And actually this is the development board. But actually if you remove these things, and so you have only this module, SOM. So this is actually not nano, but it's still very small and low power. And actually it runs on 2 modes, 5 watt and 10 watts. So it's very low power. So I mean, later Ben will describe like how we run this on using a battery only on the, I mean, the field. So yeah. So if you have any questions, so please, we can check.
Yeah. Yeah.
So there is a question about TensorRT, but I think you answer at the same time the question I asked. So yeah, we try to use TensorRT because it's really optimized for JSON, but we have some problem in computing the model because ops are not supported.
So there's one another is additionally, is there a specific reason not to use quantized model? So actually TensorRT is the quantization framework, which convert the model into floating point 16 or a integer 8-bit. So we are working on that.
And there's another question about the retraining, the lower image resolution. I don't know if Alicia calculates the new map.
Yeah, of course, it was not that good as before, but let me check and let me share the exact values.
Yeah, I think we didn't. Yeah, right. Like, I mean, we just did a visual inspection of the output of the model, right? Like, and I think maybe we can check the scores later. What exactly, how much precision drop was there after converting to edge? Yeah. There was also this question from Mayank, right? Like about NVIDIA's Deep Stream, which I think Naveen was also interested in, right? Like you also mentioned the same thing previously about Deep
Yeah,
Stream.
actually, that is in our, future things
Yeah.
we are want to explore. So deep stream, yes.
Yeah.
And for the later question, yeah, we use virtual environment also. Yeah, where we think like at least I personally think it's the best one for Jetson Nano because it's fast.
Okay, so Jetson Nano uses an ARM architecture. This means that many useful tools such as Conda, Docker are not available natively. No, I mean Docker are available, Conda is available. So it doesn't matter. I mean, if there are some packages not available, you can anytime compile that, right? But I have seen like the Docker are available from NVIDIA, and I am not using Conda, but I believe that will be available. And I did a project on Jetson Nano lately and ended up using virtual. So maybe, last year actually when I started working on Jetson Nano, many things were missing. But recently NVIDIA added with the Jetpack 4, they have 4.3 actually. They have added many functionalities. So maybe you should check out again. So maybe you can find.
Yeah, maybe we can share the link of Jetpack in the Slack channel for reference. Yeah.
It's in a Git.
Okay.
It's 4.4, I think.
For the next part, Ben will explain about the physical and the product related prerequisites for deployment. Yeah, Ben, take it over.
Okay, so then again, I will explain about, like UV said, about what actual deployment we actually did for the test field and what was the product philosophy behind it. So you can go to the next slide. Okay, so everything is summed up on this slide, so maybe try to go fast. So as Naveen explained, we deploy on the Jetson Nano because it's kind of convenient and really straightforward for POC. We run the default mode, which is 10 watt. For the power related issue, so to power the board on test field or on field, we use a 3S LiPo battery, and after conversion to 5 volt 3 amps, we power the Jetson with this 3 amps, and this allows us to run the model between 2 and 3 hours, and probably more, but we build up to 3 hours. Concerning the setup, so we use both USB and CSI camera. Because we use USB camera because the CSE connector in my Jetson was broken, but we have both solutions, and the differences between the latency is quite similar. So USB doesn't make you too slow, in fact. And one good practice I adopt is to set up your Jetson or any device you bring to the field as an access point, which is really convenient for developing and debugging when you're in the field. And so the idea was to make a product so we can have like kind of real application. So to do that, what good tools is if you have the luck to have a 3D print and 3D printer to design like a casing and to kind of try to adapt your edge device to the application you want to build. So the philosophy behind this, the message we want to send is like not just deploy to deploy, but deploy with application in mind. That's mean like, oh, we could just deploy on the Jetson on the desk and we say it's finished. But the fact is like, if you have the application in mind, it will bring your project and your idea very more impact and power. And you will also learn a lot about other engineering fields, not related directly to AI, but also like skill up all your pipeline development and application. Like for example, CAD design if you want to 3D print some part, or like Linux setup, or like electronics to review some electronics. So this is kind of message we want to use and we want to pass with MLT Edge Lab is like not just do AI for AI and AI for AI on edge, but find some application and deploy. So this really bring you more impact and more skills. So if you're in this mentality, you should join us for more projects. And so yeah, here's a picture of the Jetson. I have it here too. Yeah, the casing and the fixation for the bike was this. Some broken, so the design is still in review. And here was the camera. And for the power, we use this kind of 3S battery. I'm a drone engineer, so this is a drone battery kind of. And yeah, that's all for this slide. But yeah, bring application. It's make your project cooler, I think. So next slide. And so yeah, what was the performance and the limitation on this device we selected and we worked hard on? So like Navin said, we were able to run inference at under 1 second. So it's much the requirement for the competition kind of for the real time. And for the with the tracking integrated, we go to over 1 second, 1.2 second while tracking 3 to 7 objects. What good surprise we had with this test field is with the help of having a bulky, like not edge network, the detection were even good and blurry images. So here on the left corner, you can see some images on the detection, and some were really blurry, but still able to detect some pedestrian. Yeah, so this was, we didn't have time to tune the model with a new resolution and all the parameters like NMS threshold and threshold for this model, but we are still working on it with the data we acquire from this test field. And the last point I want to share is maybe the most important, I think, for AI on edge deployment is on the left corner. So even if you can think like like having a training data set on cars and putting this model you train on a car video to a bike, it's really similar problem because it's still moving vehicle on the road. In fact, the vision domain is still different. So the illustration I found, it's quite, I think, funny, is like in this model on edge, we kind of detect a lot of time legs as pedestrian. And this comes because even if it's quite similar problem, the domain vision is different. So for example, in a car, you will never see legs of pedestrian or close-up pedestrian. But on a bike, when you ride the bike, you will get close to the pedestrian, and this will kind of mix the domain vision and make this kind of bad prediction. The lesson to learn here is like, so it's great to have to train on the big internet data, to have a POC, but if you want a robust solution, you always have to train on edge device data set you acquire from the edge device himself. So you really fit the domain as a data domain of your edge device. Yeah, I think this is at least the most important for me point for deploying is to have real edge data. And the main limitation, right? Because it's quite hard to get. Yeah, I think that's all for this small deployment. Yeah.
Yeah, right. That is true. Like, it's so important to have the real edge, real data, if you want to really deploy an edge device, because of all these constraints, like physical constraints, mechanical constraints, like the vibration. Mm. Mm. Okay. Yeah. So. Uh, please let us know your question. So there were some couple of questions actually. Okay. Okay. Alisher already shared the result of the MAP. What was the new MAP after running the model? Wow. Cool. That's nice. Okay. We have one question from Mayank. What was the exact model of the camera? Um,
So for the CSI camera, we use the Raspberry Pi camera, I guess. It's
Yeah, so
Navin
the
who did it.
version, it's the, for the CSI camera, we use Raspberry Pi camera, version 2.
mhm.
And for the
What-
USB camera, it's USB camera I had on my desk for a while, so I don't know the model. I will search. It's kind of good quality camera, but we reduce the resolution for the acquisition a lot. I will share later. Sorry,
Yeah.
the sticker is broken.
Yeah, and you also made this casing for the camera also, right? Like to mount the camera inside. This is a 3D printed box.
Yeah.
Yeah. Okay. Any questions? Anyone? I didn't check Slack. Let me check Slack. Are there any questions on Slack or any comments? Nothing. Okay. Uh,
Yeah, just like to ask, did you guys inference each and every frame, or uh, you guys had a loop that missed a couple of frames, or for faster inference?
No, I think it's a good solution to have just if you know like you're running at 1 frame per second, you just skip a frame so you don't miss a lot of data, and to be smooth. But no, we just influence each frame because we tried just to deploy what the competition asked us to do to deploy an edge. So the competition requirement was to have one loop of 1 second, which is detection and tracking. So we try to match this on the Jetson.
yeah, but for maybe for like I mean, so you suggest like yeah, if we skip this, it might be more faster. Like I mean, from inference point of view, right?
Yeah.
To use skip some frames because it's the same content over and over again. Yeah.
And one more query. And did you guys have some sort of a? I'm just thinking out loud, but to improve this further, maybe the blurred images that are fed into the engine can be detected based on the accelerometer if you have any, and only the stable images can be applied, or some sort of a computer vision algorithm can detect the blurred images and pre-process it, or cut those frames so that it is not inputted to the how do I say it, the pipeline.
Yeah, maybe Ben, yeah, you are good with that.
Yeah, in fact, it's a really good idea, and I'm using that in other project, like to detect blurry images, and if it's blurry, you don't feed it to the detection. Yeah, that's a good idea. But here we are really kind of really like, because the model is really huge, we are kind of running maximum capacity right now. So we will not be able at this we will not be able to run a previous model for detection blurry or not. If you want to detect if it's blurry or not by AI. If you want to detect with accelerometers, I think it can be tricky because you're on a bike, it's moving, and the movement of the camera and the blurriness of the lens maybe not reflected directly from the accelerometer data itself, I think.
Ben, if we were to do that, like what kind of setup would you recommend? Like, I mean, yeah, we didn't do in this project, but say if anyone wants to think on that terms, like how to remove the blurriness or how to improve that vibration, how to remove that vibration point, what are your suggestions or recommendations?
So you have physical solution, right? So you can go just by small damper on the camera to avoid like vibration. Or you can go to the gimbal, having a gimbal on the bike if you want to spend a lot of money and resources for that. On software side, I think you can have some basic computer vision filters that would kind of classify as it's blurry or not. Or you can really have like just a specific small model that classifies the frame as not blurry or blurry, I think. But physically, a material, you can have a better camera fixation on the bike.
Okay. Yeah, there was like one question related to the same topic, like, is this blurriness detection fast enough?
We didn't implement it here.
Yeah. So you use it in any other projects in your site, right?
Yeah, but yeah, right now it's too slow.
Okay, I see. Okay. So there is a scope of improvement on that part also,
Yeah,
like
there
to
is
remove that physical constraint. And yeah, right, like so either you fix these kind of like issues when it comes to deployment, either physically, like try to optimize it using some kind of like engineering way, or you totally delegate all those problems to the software part, like to the model to come up with that. But for that kind of solutions, it's still like the models right now are maybe in still like not that good performance state, which might be a point of improvement in future. Yeah. Okay. Yeah. So I think that summarizes, and I mean, we have come to the end of the slide, most of the entire discussion. Like these are all the things which we did in these 2 months working on the competition. Finding this competition was actually, if we look back now, it was really helpful because with competition we had a goal to win in the competition, and then it gave the extra stretch goal for us to go beyond the competition and deploy it on the edge. So this is another learning for us, like participating in this kind of like open competitions and forming quick teams is quite essential to work together. uh, I think every member has some kind of like take away from this competition, like not just you are not limited to your own domain, like Ben had mentioned it, like you get to learn about so many other engineering skills apart from just the software part. So that's quite important. With this slide, I would like to throw some topics to the Edge AI Lab community here. The topics which we are interested in working in future. Uh, like the first one is like the DeepStream SDK. I think even in the chat, someone had mentioned about the DeepStream SDK, and Naveen also mentioned like he is quite interested in working around this area. So to give just a quick one-line description, what DeepStream SDK is like, it is a SDK to help you to deploy the video processing pipeline directly on the GPU instead of using the CPU overhead. So traditionally, when you have a camera, your camera feed goes through CPU, and then it is then thrown to the model, and everything goes by the CPU loop. So in DeepStream SDK, I think everything is deployed directly on GPU. I don't know in detail about that, I think, but yeah, we might be interested in doing any project around that part. Another topic is like the FPGA topic, which I'm also like personally interested in this part, and some members also. It's a technology where you can put your model directly on the hardware circuit and deploy it on the chip. This is like converting your model totally to an electronic circuit and then running it directly as a real physical electronic chip. So this is expected to be much more faster than CPUs and GPUs. So it is, but the problem with this technology is like it is still like the documentation or the obstacles which are present to deploy on FPGA are a little bit higher. The learning curve is a bit steep. It's long. So that's the problem with FPGA. For TinyML, TinyML is another domain which we want to explore. Is like which focuses mainly on building machine learning models on low power, ultra low power systems, which use just milliwatts of power, and you run a model on top of that. So that is also another topic, and there are other topics also which we would like to discuss or maybe actively think in the community to make some kind of like project or participate in any kind of this kind of competition together as an MLT part. So going with that, so we have open source our entire source code on MLT Edge AI contest repository. So please feel free to check out our source code. Also, please feel free to use the source code and build your own applications by yourself. If you guys are interested in any kind of like this idea on top of this particular idea, like we thought of real life application as a bike application, but you guys might have some other application apart from bike. So if you want to reuse the source code, it's definitely better for us because you don't need to work from scratch. You can use this source code and then build your product on top of it. We can support each other, and then if we can form some team, it's nice. We have also the details are also mentioned on the blog post. So if you want to take a look at the blog post, you can check the links there. So I think we already past 4:30, but yeah. So let us know your feedback and any suggestions for Edge AI Lab community or any topic which you would like to work on or interested in. So we might have some good teams around in the Edge AI Lab community. I think that's it from my side. Any of the members, any last comments from Edge AI Lab team? Anything? Or Susanna, do you want to give any comment? Or...
Yeah, no, thank you so much. I just wrote in the chat that
sorry, yeah.
For congratulations to the great results. I don't know, like, I hope that people know that 2 months was a very tight schedule and the team did an absolutely amazing job. I've been by their side and supported and overlooked it, and you did absolutely amazing and great results. And yeah, it's a lot of fun, and I just want to encourage people to, you know, if you like to work on hardware, on Edge, please send a message to Yuvi, join the Slack channel, Edge AI Lab. And yeah, there's plenty of opportunities to work on hardware projects. It doesn't matter what kind of skill level you have, what kind of background, as you've seen, like for hardware projects, there's always different skills needed, right? From EDA to software to deep learning to hardware, there's a lot of things. There's a lot of exciting applications, I think, in the Edge AI space. And if you're interested in working on it, just join the Slack channel and we can provide the platform for it. And that's it from my side. Thank you so much, guys. This was great.
Yeah, thank you, Susanna, for your comments. It was really helpful for, like, you helped a lot for guiding to the project, what to do, what not to do. And I think it really helped us to achieve this. Okay. So I will keep this channel open for maybe a couple of minutes, 5-10 minutes. If anyone has any comments or any thoughts or suggestions, feedbacks, anything, just as a casual chat. So you can unmute your mic and we can have a casual chat right now. But as for the presentation workshop for the meetup session, it is finished. So thank you for your time. Thank you everyone for your time on Saturday holiday. So let's keep in touch on the Edge AI Lab Slack channel.